All right, let's begin the third session now. Thank you all for coming again. Let me see if everything works. Yeah. So the past two sessions, we saw introduction to numerical methods, particularly about deep neural networks and what deep learning is about and how it's useful as function approximators. We compared it with different existing methods and we learned some optimization techniques in high dimension. And we're going to use the tools that we saw in the past two classes to solve a macrofinance model with aggregate shocks today. So here are the references. Most of the material today will come from my working paper, but here are a couple of other useful references. And the last paper by Jesus Fernandez Villaverde and co-authors particularly focus on solving models with financial frictions. So you can take a look at that as well. Okay, so what is aliens all about? The whole idea is to use neural networks to solve general equilibrium continuous time models to capture global dynamics. These kinds of problems appear in many areas of economics, particularly models involving some form of portfolio choice, continuous time models with monetary policy example. For example, the portfolio choice problems go all the way back to Merton 97, and there are other problems by Two Trees by Cochrane and co-authors 2008, and Lucas Orchard by Martin 2013, etc. More on the macrofinance side, you're all familiar with these models because I assume most of you took Econ 529. And there are some new generation macrofinance models with focus on monetary theory as well. The whole idea is to use neural networks to solve these classes of models. How are we going to do that? We'll use economic information as regularizers that will guide the deep learning algorithm in solving these equilibrium classes of models. And specifically in high dimensions, it's too costly to draw lots of sample points from throughout the state space. So sparsity in this technique is achieved in two steps. First, you draw sparse sample points from throughout the state space, and then you pad those sparse points using active points, where these active training points will come from areas that matter the most for convergence. I'll focus some time on what this active learning is about and how this can be useful, especially when you solve models in high dimensions. All right, so here's a general setup. Assume a representative agent economy. The agent maximizes the expected lifetime utility. I denote the utility in general as this aggregator function here because this also nicely captures recursive preferences as well. But if you want, you can think of this just as a CR array utility, C power 1 minus gamma over 1 minus gamma that we are all familiar with. The agent maximizes lifetime expected utility in order to solve for optimal policies. Let me get rid of this. Yeah. It's similar, but these recursive preferences are basically the continuous time version of the what's it called, Epstein-Zane utility functions. The whole idea is that when you use CR array utility function, the intertemporal elasticity of substitution and risk aversion become intertangled. In order to separate these components out, richer preference structure is required, and that's where recursive preferences are very helpful. The recursive nature can be seen here. Your UT depends on US, right? But this is basically the continuous time version of Epstein's preferences. Not really. Not really. You could just use CR array utility function. All right. There is exogenous dividend process of a risky asset. The evolution of this risky asset follows this differential equation. Z is a standard Brownian shock. Sigma is the exogenous volatility, and G is the exogenous growth. For now, assume sigma and G are constant, but later we'll think about what happens when these two are time varying, because the state space is going to expand. All right. There is also a risk-free debt market that pays a return R. The risky asset has a market price of risk, zeta t, and some volatility. And these objects, problem is very simple. The agent maximizes the lifetime expected utility in order to choose the optimal consumption and portfolio choice theta. Okay? Wealth evolution follows this equation. The agent earns risk-free rate R as the portfolio choice theta, earns market price of risk, consumes out of wealth, and the wealth is affected by the return volatility, which is scaled by the portfolio holdings theta T. Okay. This is a fairly standard problem. Now imagine in this case, if sigma and G as well as R are time varying, then we suddenly have a multi-dimensional problem. Okay. How do we solve this problem? This is formulated in continuous time. So you write down the optimization problem, the HAB equation, and that is nothing but maximum of the utility function here, which is this aggregator, plus the expected increment of the lifetime utility. And here you immediately notice the power of continuous time technique. When you have discrete time model, here you will have ut plus 1 minus ut, and computing that expectation introduces additional curves of dimensionality. Whereas here in continuous time, you can just apply Ito's lemma to ut, and once you apply Ito's lemma and take expectation, all the shock term disappears because expectation of the increment of Brownian motion is 0. And what you end up with is a deterministic partial differential equation to solve. Okay, once you write down the HAB equation like this, and you do some algebra, and you arrive at an equation like this. Now, what is this nasty equation? Here is the function that we are solving for J. You can think of this as the value function or the stochastic opportunity set, but um, let's think of this J for simplicity as the value function. Okay? And the PDE coefficients here, this is a partial differential equation because the state space X can be high dimensional, right? And the parts in red are coefficients of this partial differential equation. This is typically called as the linear term. U is some function that's dependent on the state space X as well as the function J. And this can be endogenous because the state space X can be endogenous, and J is the function that we are solving for. Because of that dependency, this is endogenous, as well as this can also be a highly nonlinear function. This is known as the advection equation. It enters before the first partial derivative with respect to the state variables. That can also depend on the state space X as well as the value function, can be highly nonlinear. Okay? And this term is called as a diffusion coefficient. Remember, all these terms are actually functions. Okay? Especially when they are highly nonlinear functions, then this is a highly nonlinear partial differential equation to solve. When closed form solutions are not available, it can be difficult to directly solve this nonlinear partial differential equation, especially when the number of dimensions is high. All right. Now, one common technique that's used in the literature, which is borrowed from fluid dynamics, is called false transient or pseudo transient method. What it does is that it introduces an artificial time derivative in this differential equation here. Now, if you notice this equation, you don't have the time derivative, whereas this equation, you have this time derivative. If you've taken econ 5 to 9, you're probably very familiar with this. But for the others, more broadly, what this does is that this makes the whole scheme iterative. What you're doing is you're converting these unknown coefficients into known coefficients. Okay? What it does is it essentially freezes these coefficients as known constants. And therefore, you now have to solve a quasi-linear parabolic PDE, which takes the form 6. All right. This you could discretize this equation 6 and solve using finite difference methods. But now there are a bunch of papers which show that even when the number of state variables is just 2, especially when the state variable is correlated, it becomes difficult to maintain monotonicity of these finite difference schemes. I won't go into the details, but you can look at this paper here, which has a description of why that problem arises and how that issue by augmenting the plain vanilla finite difference method. What we will do today is, instead of discretizing this PDE, we will just encode the function J as a neural network object. All right, so here's the overview of the methodology. Focus is to solve models where the value, the HAB equation reduces to a quasi-linear parabolic PDE like this after the introduction of artificial time derivative. So let's look at this figure. What you do is you start with an arbitrary value function j, and you compute the PD coefficients by computing these policies. What are these optimal policies? They are consumption, portfolio choice, capital price, return, and the diffusion and advection coefficients here. Okay? Now, look, this is very general. You can have any type of portfolio choice problem or macrofinance model. These are going to be your optimal policies. They can either be available in closed form up to j, in which case it's trivial to compute these quantities. Otherwise, you could just use some numerical techniques. In cases where closed form solutions are not available and uh, simple numerical techniques are infeasible, they can also become neural network objects. Okay? For today, I'm not going to focus on that. Today, I will only focus on how to solve this partial differential equation using neural network. But if you want to encode this as neural network objects as well, then it's perfectly fine. All right, once we solve for the value function j by using the neural network technique, data these policy functions, and we go on in an iterative fashion until the error in j is very small. By that, I mean that from one iteration to the next, the change in the value in absolute max sense should be as close as possible to 0 as you want. All right, that's the overview of the methodology. How are we going to do it? Let's go back to the partial differential equation that we had. This is the equation that we saw before. You had this artificial time derivative. You had the advection term here, diffusion terms here, and the linear term. D can be high dimensional, and the goal is to solve for is to find this approximation j hat that satisfies this partial differential equation in the time-space domain. Okay? As well as it has to satisfy the initial condition in the time boundary. Right? Is this clear? Okay. Because of the introduction of artificial time derivative, we are making this whole scheme iterative, which means that we have far more restrictions here. One is that this PD has to be satisfied in this time-space domain. Right? K here denotes the number of iteration. For example, the first iteration, we would solve for this PDE in t minus delta t to capital T. In the second iteration, you would solve from t minus 2 delta t to t minus delta t, so on and so forth, and throughout the state space. Okay? For the time dimension, it's going to be randomly sampled as well. Yeah. Well, not only that, it also has to satisfy the initial condition, right? In the first iteration, it has to satisfy the initial condition in the domain capital T across state space omega. Omega is the state space. Omega is the domain of the state space X, right? Cool. So we will encode this j hat as a neural network object with parameters theta, and this f is known as the PDE residual. And the goal is to have this PDE residual as close to 0 as possible. All right. So if you stare at this problem for a while, it is very close to some optimization problem that we are all familiar with. For example, the goal is to find the optimal parameter theta star, which minimizes the data fit. This j tilde is the initial condition. It minimizes the data fit such that it also satisfies the condition that the PD residual should be close to 0. But what does this mean? F cannot actually equal to 0. So it's close to 0 in some L2 norm sense. Okay. You still have the data fit, but for the PD residual, the mean squared error in the PD residual should be close to 0. All right. Empirically, this mean squared error is nothing but you draw lots of sample points for time dimension as well as the space dimension, and you feed it into the PDE equation here. You compute the residual, and you compute the mean squared loss of that residual, and that should be as close to 0 as possible. That's all this equation is saying. This x is just the state variables of the problem. And you also have the time dimension here, right? And this j will receive as inputs all the state variables x as well as the time dimension t. Here. Oh, this is like a static equation. Here there is no time dependence. For example, once you compute j, you use that j to update x, right? So the artificial time derivative is only there to update this j, right? This equation will be satisfied in this time domain at every iteration, right? So you update the value function j hat. Now, once you found a new j hat, you use that to compute those PDE coefficients. So that's why there's no time dependence. So this why is this better than finite difference methods in high dimensions? When you use finite difference methods, you typically have to carry around a grid, and that can be painful. For example, if you have 3-dimensional models with 100 points in each dimension, you already have 1 million points, and that causes a huge drain on the memory. This technique here is mesh-free, and what does it mean? That you just randomly sample points from the state space x as well as the time dimension t to train the neural network. And in fact, you don't need a lot of points. You don't need 1 million points when you have 3 dimensions. You can just randomly sample, say, 2,000 to 3,000 points and just iteratively solve using stochastic gradient descent or variants of stochastic gradient descent that we saw on Friday. And that's the goal. And that's why it's better than finite difference methods. However, when you have like 5 or 6 dimensions, still, it's important for you to capture training points that come from economically most relevant regions of the problem. So, yeah. Oh, yeah, sorry. That shouldn't be there. But in some problems, you have a reflecting barrier at the bounds of the state space. That just means that at the boundary, right, at this boundary of the state space, the derivative should be 0. So that's why it's there. But it doesn't matter. So let's just focus on these 2 equations. Probably I should just remove this. It doesn't, well, 0 is an example, but it can be anything, right? Depends on the problem that you have. If you have some condition that gives you, oh, this is not this one. This is J0. It's not J tilde 0. Sorry about that. Yeah. J tilde 0 is the old value. J0 is some value that you have, some other value. Yeah, they're not related. Yeah, yeah. In fact, we're not going to use this today. Mm-hmm. When I compute the PD residual, I would also use this one. Mm-hmm. With mm-hmm. Yeah, in the end, it's going to be 0 anyway. But in the beginning, that's going to be huge, right? That loss is going to be large. And well, the idea is that let's think of a rectangular grid where you have x here and t here. And this PD basically has to satisfy throughout this grid, throughout this sample space. That's mainly used for stability reasons. When you introduce this artificial time derivative, you're basically slowly introducing the nonlinearity. And when you introduce this time derivative, you're basically, that also automatically implies that we have to satisfy this condition, right? It's like you're forcing to learn at the time boundary as well as throughout the time plus state space boundary. All right, so let's focus on the sampling part. So how do we achieve sparsity when we have 5 or 6 dimensions? The idea is that you just sparsely sample from throughout the state space, but then drawing lots of training points from the entire state space is way too costly. So what you do is you draw very sparse points, but then you augment those points by looking at some subdomain omega c that carries the most economically relevant information. Okay? In problems related to macrofinance, or most of the problems that you solve in that you saw in Econ 5 to 9 had some region where there was fire selling happening or some crisis occurs, and this region could be very important for the algorithm to capture accurately in order to ensure convergence, right? So because of this time marching scheme, because of this iterative scheme, once you solve for the optimal policy, it gives you some information about where the economically relevant regions are. That allows you to track this subdomain omega c from one iteration to the next and draw these active training points. I think I have a couple of slides with a concrete example, and I'm hoping it's going to be much clearer there. But the whole idea is that first you draw some sparse sample points from throughout the state space, and then you augment those points from subdomain omega c, which can be a very small hypercube in a high dimensional space, right? But it's important to capture that small hypercube and draw enough points from there if you want to ensure convergence faster. Let me show you an example that will make it very concrete. But before that, let's look at how. Let's assume that we know how to draw sample points, okay? And then we are going to use this neural network approximation J hat in order to solve this problem. Okay? Lots of equations here, but let's just go one by one. This is the familiar equation that you know. It's just a partial differential equation, where J hat is a neural network with parameters theta. Right? It has to be satisfied in the time space domain. You also have the initial condition here that should only be satisfied in the time boundary. Okay? If you notice here, it's only at t minus k minus 1 delta t. It's not throughout the time domain. It's only at the boundary. And that's why it's a boundary condition. And this is for the sparse points, but you also repeat the same for the active points by inspecting the subdomain omega c. Okay? All right. Once you have that, if you have some knowledge of reflecting barrier, you could also impose it like this. This J is 0 is some value that that can be 0 if you have a reflecting barrier at the boundary partial. Well, let's call this time bound space boundary. Okay, so this is how the neural network object is going to look like. We saw how to draw sample points from X and T. And once you have that, you just feed it into a deep neural network object. I think by now you're all familiar what this object is here. This is a fully connected feed-forward neural network. You take the points from the state space, you feed it into a nonlinear activation function sigma, which is a tanh activation function in this case. You take the output and you feed it into the next layer and you compute J hat. And if you go back to the first lecture, this is going to be like aggregation, then activation, aggregation, then activation, so on and so forth. Okay? Here, there are just 2 hidden layers, but it's important for the activation functions to be nonlinear. All right, cool. Now, here's an example from one of my papers where active sampling can be very helpful. Let's think of the grid here. This is a 2-dimensional problem. One is a Welch share of the intermediary. Second is the productivity parameter. If you're familiar with the model from Econ 5 to 9, this is some variant of the model that you saw in a handbook chapter, where Welch share of the experts is an endogenous state variable. But in addition, you also have another state variable here. And so it's a 2-dimensional problem. And if you were to use finite difference methods, you would use the entire grid like this. There are lots of grid points on Welch share dimension because it's an endogenous variable, and some sparse points on the productivity dimension. The optimal policy is going to look like this. For example, this is the capital price as a function of the Welch share and productivity. And you notice that in good states of the world, price is high, and in bad states of the world, it's low. Now, if you were to use neural network method, how would you sample from the grid? Okay, first you use some arbitrary value function and you compute the PDE coefficients. If you inspect PDE coefficients, you can learn this active region here. So how can we achieve sparsity and ensure convergence? First, you draw sparse points from this grid. And you don't need to carry around this grid at every iteration. You just randomly sample in a uniform fashion here. And then you inspect the PDE coefficients and you learn that this is an economically relevant region where there's a sharp transition from one part of the state space to the other. And you track that subdomain omega c, which is this, and you draw more points and you augment it to the sparse points. And this becomes your active region. But why is it active? Because this is an iterative scheme, which means that from one iteration to the next, not only the location, but also the shape of this economically relevant region may change. Now, this is a relatively simple two-dimensional problem, but think of a five-dimensional problem where there is even no way of visualizing where this small hypercube is, right? This red points here, this region here is like omega c, but if you have a five-dimensional problem, this can be a very small hypercube in this high-dimensional space. But what this active learning does is that it actively, from one iteration to the next, automatically figures out where this hypercube, where the small hypercube omega c is, and it'll draw enough points from that omega c and augments it to the sparse points that will ensure convergence. So that's the idea. So that depends on the problem at hand. So in this problem, it's the relevant region is kind of the fire selling region, if you want. But in other problems where you don't have any economic information, what you can do is you can track the error between one iteration to the next, the error in the value function, and you see where the error is the largest, and you draw more points from there. They may not be economically relevant. They may be, but they may not be as well, but they may be computationally relevant. Okay. This active learning ensures that you're still drawing from computationally relevant regions to ensure convergence in a faster way. Okay. Yeah. Yeah, that's right. It turns out that in this problem, the kink is mainly coming from the well-shared dimension. So you do active learning in that dimension. But in other problems where there are non-linearities coming from both dimensions, then you look at both. Okay? And these are the rules that you kind of artificially impose as an economist. But again, if you don't have any of this information, just look at where the error is largest. In many cases, they are correlated. Economically relevant and informationally, computationally relevant regions are correlated. But yeah, that's the question. Yeah. This is for the time iteration, right? There is also the stochastic gradient iteration. So in that stochastic gradient iteration, the active points remain fixed. It only changes at the time iteration level. Okay. In finite difference, you could. Yes, in finite difference you could, but I think the problem is when there are disparate regions, then the approximation of the derivative will not be accurate. If one of the active regions is here and the other active regions is here, and you don't have enough points here, but you have lots of points here and lots of points here, and you take finite difference, then the approximation error is going to be very large for the derivative. Whereas here you're going to use automatic differentiation, and that reduces the approximation error. And what's nice here is that because we are using neural network methods, it also works regardless of the shape of the subdomain. And this again goes back to the first lecture where we compared neural network solution against projection methods. If you have an irregular shaped boundary, you can still use active learning and everything works fine. But if you use projection methods when the state space is irregular shaped, then typically there are problems in convergence. Yeah. Not really, because once you compute these active points, you just use stochastic gradient descent to solve for J, and then you forget about these active points, because the next step is to update the PDE coefficients using J, right? And once you have the new PDE coefficients, you again fish for active points. Yeah, that's true. That's true. There's always interpolation, but what I'm saying is it has nothing to do with the active points, right? Once you train the neural network, then you could have a grid if you want, and you can just find the value J hat at that grid by interpolating. Okay, but at that stage, the active points become irrelevant. It's just to make sure that the PD residual is close to 0. Okay, so now that we know how to sample, all we have to do is just compute this J hat and then impose PD residual as the economic as the regularizer in disciplining the model. Okay. How are we going to do it? For the partial differential equation, all we need is the partial derivatives, and that's where automatic differentiation is very helpful. Once we have J hat, we just compute these partial derivatives using autograd, and then we compute the residual here. How can we do that? Well, because we know these advection and diffusion coefficients already, because they're computed using J old. And we also have J hat from the forward propagation, and we have these derivatives by these derivatives here from the automatic differentiation. Just use all of those objects and compute the loss residual. And this has to be satisfied in the time-space domain. Here, I'm dropping K to avoid cluttering of notation. But basically, this whole algorithm should be repeated for every time iteration. Okay? And here I have the right notation. This J hat should be J old in the time boundary. All right. And the previous slides, this was J tilde 0, which I'm going to fix soon. Right. If you have active points, you can also do that. You can also repeat the same thing in the active points. And all you have to do is just aggregate all the loss components and then minimize this aggregated loss using Adam optimizer. Okay. Now, if you go back to the very simple examples that we saw on Friday, this loss was basically mean squared loss. Data points to fit, and the loss was just mean squared loss. But here the loss is quite complicated. The first loss, this loss is very easy. It's again in a mean squared sense. But this loss is like a PD residual loss. This is also means L2 norm, but still there are lots of things going on here. It's not as simple as just fitting 2 data points, but all the principles remain the same. In this algorithm, first you have to define what the neural network is. Okay? Then you define the loss functions, and you define the optimizers that you want, and then you just compile the model, and it's going to fly. Okay. I will show you in exactly how it's done in TensorFlow. But what's important to realize here is that when you compute these automatic differentiation, the operations don't happen when you compute these guys here and these circles. What's happening here is that the moment you do this, some computation graph gets created in your memory, and finally you can just pass in as many data points as you want and then execute those at the same time. Okay. And that's how it's different from the conventional programming that we know in MATLAB or Stata. Okay, so here's the aggregated loss, right? You have the PDE loss, you have the bounding loss. This is like the data loss. And you also have the same things from the active regions. Okay. Now, there are other techniques in yeah, it's the same loss. You could, just combine this NF and NC together. But just for clarity, I just have it as 2 separate regions. Okay, so there are other techniques in macro finance and machine learning literature. For example, some of the papers use ergodic density to draw training points. I don't know if you're aware of these papers mentioned here, Zinovich and Simon Scheidegger 2018 and Fernando Villaverde and Coates 2020. What they do is that they first solve for the ergodic density of the problem. Let's go back to a very simple example that you saw in Econ 529, where there is a household and an expert fire sells household in bad states of the world, and that causes financial amplification. In that model, the only state variable is the wealth share of the intermediaries. So let's assume that we would want to solve that model using the techniques shown here from these papers. What we do is that we would solve for the ergodic density of the state space, which is the wealth share of the experts. When we solve for the stationary density, this is how it's going to look like in the dotted line here. Almost all of the points lie near steady state. However, what I show here is the policy function. Well, not policy function, but return volatility. But if you plot some policy function, that's also going to look something like this, where there is high nonlinearity that happens in bad states of the world. Now, if you were to use this stationary density to draw training points, almost all of them are going to come from the most boring part of the state space, okay, which is near the stochastic steady state. Okay, so a better way to solve these kinds of models is that you draw training points uniformly from throughout the state space, and especially in higher dimensions, you make sure that you have enough points from the extreme left tail of the distribution. If you're solving for models with inequality or something like that, where lots of action also happen in the right tail of the density, then that also becomes economically relevant. Okay. Now, if you just use the ergodic density to solve this model, it's like linearizing around the steady state. You're not going far from that. It's not really solving for the global dynamics, especially when the constraints bind far away from the stochastic steady state. Okay, so let me quickly show you how automatic differentiation is done in practice. The first thing was to define the neural network object. In TensorFlow, that's trivial. I'm going to use TensorFlow 1 notation, but it's the same in TensorFlow 2 with some minor differences, which I'm going to explain when I show you the code. Basically, in just one line, you can just define this neural network object. You can specify how many layers you want and what kind of neurons you want, everything into this function neural net. Once you have defined this object here, let's go back to the previous figure. Yeah, once you have defined this object in TensorFlow, what you have to do is use automatic differentiation and compute this loss residual. And let's assume you have a one-dimensional model. Then this is the loss residual that you want to compute. Okay. Sorry, you can't see, but the slides are in the Google Drive folder. You can just open up and inspect what these are. This is basically a quasi-linear parabolic differential equation just in one dimension. One space dimension and one time dimension. Okay. Now let's compute the PD residual F. It takes as input the state variable Z and the time dimension T. Here's how you define this neural network. That is, you're calling this object here. And computing these derivatives are very cheap because you just automatic differentiation. Okay? You just call TensorFlow dot gradients J comma T. What this means is this is basically dj over dt, partial dj over partial dt. Similarly, you do the same. Also, the second order derivatives can be computed like this, and you compute the PD loss F. Now, this is a simpler one-dimensional model. What do we do when you have a two-dimensional model? Oh, yeah. These advection and diffusion, they are functions of Z as well. Yeah, exactly. That's correct. These are like coefficients, but they're like functions. All right, so what do we do when you have 2 dimensions? Well, it's the same thing, except that it now takes 2 variables, z and a, which are the state variables, and the time dimension t. Okay, and then you use the same tf dot gradients to compute these derivatives. Okay? Once you do that, you just compute the PD loss, and you assume that these advection z, advection a, so on and so forth, these advection and diffusion coefficients are all computed using J old, right? And so this is your PD loss in 2 dimensions. Now, when you have 100 dimensions, doing this is very inefficient, but you can always loop through. Like you can have an index and use that index to compute these derivatives, and finally the loss residual. Okay, half an hour more. So I think let me stop here, go to the code, and then come back to data parallelism if we have time. The file is called BCF Model 1. Here's a bunch of libraries that I'm importing. If you're going to use Colab, then you don't have to have TensorFlow installed in your computer. This is going to be done automatically, assuming that you followed the instructions that I gave you on Friday. It's not the same as this one, because here you're just importing, but you still have to install TensorFlow on Keras. But I think we already saw that on Friday. You can ignore this bunch here. This is for if you already have some expertise in Python, and if you want to run directly from the terminal, you can use these flags. But if you just want to use Colab, then forget about these. This file basically has 2 classes. The first class is where you solve for the partial differential equation, and the second class is where you update the PD coefficients. Okay, and so why am I doing it in classes? Because this is the closest thing to a library that I can build. So, for example, some people here wanted to do solve some financial stability models. Like if you have a continuous time model with a financial stability focus, and then what you can do is you can write a separate class which computes those optimal policies and computes those PD coefficients, and you can let that class interact with this class, where all you need from your main model class is the PD coefficients and the state space information. In this case, you have this is a model that you saw in Econ 5 to 9, right? So linear term E means expert, linear term H means households. You have an advection term, you have a diffusion term for each of the diffusion term is assumed to be, well, I think it's the same for both households and experts, but advection term may be different. And that's why you have advection ZE and advection ZH. What you also have is an initial condition for experts, J0E, and an initial condition for the households. You have the batch size, learning rate, how many iterations for Adam you want to run, your DT interval, and information about your state space. Okay? XPDE is state and time dimension, whereas X only has the state space. Once you provide all of those as inputs, remember in the object-oriented programming introduction, we saw what an init function is. It basically instantiates this class. As soon as you create an instance of this class, this function runs. That's what it means. Once it runs, it collects all the inputs and it assigns to the instance of this particular class. All right. We need an optimizer. So we're going to use an Adam optimizer, which is the most popular optimizer available on Toolbox today. And you remember I had 2 slides on why initializing the weights is important. Here I'm going to use Glorot normal, which is similar to the Xavier initialization we saw in the slides. To refresh your memory, it's not just enough to have normally distributed weights. We want to make sure that we account for the number of neurons in each dimension so that learning is not shut down. Right? And that's why this initialization is highly important. And you have a hyperparameter called batch size. And you have a bunch of stuff that I'm going to use later. I'm going to show you. Once you have information on the state space, you just allocate it to the class instance as well. Okay, here's how you define a neural network. You write a function, and then all of this can also be done in one line. If you use Keras, but this allows you to have a lot more control over what kind of activation function you want. And also, if you want to use the same neural network object for both the value function of households and experts, you don't want to repeat stuff, so you just write it as a function, right? This is a function that takes an input dimension, number of layers, and number of neurons. You're going to use a fully feed-forward neural network, which is what the sequential model does. Now remember, sorry, here you don't need to actually specify, you don't need to actually build the entire network yourself. All you have to do is call the Keras library, and especially the models object in Keras class, and just define it to be sequential, and then it'll understand that it's a fully connected feed-forward neural network. And you're going to add to this model dense layers. What is dense? It's fully connected. Like every neuron is connected to every other neuron in the next layer. And you have a tanh activation function. And for each hidden layer, you also have tanh activation function. And for the final layer, it's a linear layer. So if you don't specify any activation function here, it's just a linear activation function. Because you don't know what the value function looks like. Can be anywhere from 0 to, can be anywhere on R plus. All right, that's how you define neural network object. Let's define the value function. Sorry, let's define the PD residual. Okay, in the PD residual, you have two functions, value function E and value function H. Both of these are neural network objects. Okay, this is going to be defined later, but I'm just going to show you the definition of the loss function. And it also takes in the state space as input. You're going to use something called tape, gradient tape, in order to compute these derivatives. Remember in the slide that I showed you, all the partial derivatives to compute the loss residuals can be computed using automatic differentiation, and that's what's being done here. TF.gradient tape allows you to record in the memory those derivatives, okay? And that's why it's super cheap. It's like a cassette and tape recorders. That's the way to think about this. You're just taping all of the gradients here. And once you have all of the gradients, derivative with respect to z, the second derivatives, once you have all of them, you just compute the residual, right? The residual is fairly simple. You know the advection z and diffusion z coefficients. Why? Well, because it's coming from outside this class, right? You solve the static model and you just send in these coefficients, assuming that they are known. Okay. What's unknown here, what needs to be solved for, is this function u, right? What is this function u? It's defined to be the value function h and value function e, depending on the agent type. We're going to use the same function to compute the value function for both households and experts, and that's why there's this agent type. Agent type is households, then u is value function h. If it is experts, then it's value function e. All right, so this whole bunch throws you the PD residual. Once that's done, what should we do? We just need to aggregate the loss. How do we aggregate the loss? There are many components. There are 4 components that are important. First is the PD residual. Second is the loss on the time boundary, and loss 3 and loss 4 are the same thing, but for households. But let's focus on the first 2 losses. This first loss is the mean squared error. TF.reduce mean just computes the mean squared, the mean error, especially after squaring, if you use TF.square. And this loss 1, is the PD residual here. The PD residual here is computed by calling the function that you wrote earlier. Okay. If you don't follow all of it now, you can also go back to the recording. I know that there are lots of functions here, so it can be a bit confusing. But all we are doing is that we are computing using automatic differentiation, the loss residual, we are just aggregating all of the loss here. That's all you've done so far. Define neural network, define compute loss, aggregate loss. This is where sampling is done. This is a one-dimensional model. I'm just going to randomly sample from the state space. No active learning is required. It's too cheap to just sample as many points as you want. Here, I'm going to call this PD solver, where I send all of the objects and I compute the total loss as well as the PD loss. Okay, so here's the main step. This is the training step. You call this loss function. Once you do that, you apply the optimizer. This optimizer is defined to be Keras here. Is defined to be Adam optimizer here. You call this self.optimizer. Sorry, use that self.optimizer and you apply the gradients of the value functions that you have. Okay. All right. So that's the training part. If you type all of this in Google Colab, I'm going to show you what happens. Share. Okay. I think Zoom participants can also see this Colab screen. If you don't have a Pro, this is what you're going to get. Because I spoke for too long, it got disconnected. But I hope behind this disconnected screen, you can see, but maybe you can't. Let me. Okay, you can see now. This is a Colab file where you import TensorFlow and Keras. This is the stuff that I showed you on Friday. Once you do that, just copy the code that I have, that I just showed you here, and let it run. Once you run, what you would see is that training starts. Training starts, and you're in the first iteration. Okay. Losses. This is not the first. This is 47th iteration. Okay, this is the first iteration. When you begin, the loss is fairly large. It's 0.9. Not good. And this is the first time iteration. Okay. The first time iteration, it runs for 6,000 epochs. The loss is reduced to 1.9 into 10 power minus 4, which is not good at all. But then this is the first iteration. The absolute max error is around 0.57. Again, no good. But we are slowly introducing nonlinearity. The first iteration, it's not going to work out, which is fine. But then as the iteration progresses, if you notice the first value here, the first loss value in each iteration, it just keeps reducing. Okay. So this is the first time iteration, right? In the first time iteration, what you do is you start with an arbitrary value function and you kickstart the algorithm, and it's going to use Adam optimizer to minimize the loss. It runs for 6,000 iterations, where for each iteration, it is randomly sampling from the state space, and it's using the Adam optimizer to minimize this loss. Okay. And eventually, it reaches to this loss, and then I stop, because I specify the total number of iterations to be 6,000 in the beginning. Okay. We could, but there is a more efficient way to do that, and that's what I'm showing here. Okay. In the first iteration, you're slowly introducing nonlinearity, and because remember that this artificial time derivative means that we can't expect in the first iteration to achieve convergence, right? In the first iteration, it's going to be wrong anyway. So just run for 6,000 iterations. Okay. And once you have this new value function, update the PD coefficients, and then compute the value function again for 4,000 iterations. That's correct. The first block is no time derivative is the time boundary is also fixed. This iteration only refers to the J old is fixed. Yeah, in this block, J old is fixed. With the time derivative. That's correct. In here, another short step in here. Yeah, in here, it's just that small step you're using. This iteration only refers to the descending down the loss landscape. Yeah, that's it. This blue part here, it's just t minus delta t. That's it. Exactly. It's just a gradient descent. Yes, that's correct. Yeah, that's correct. Okay, so once you're done for t minus delta t, what you do, you stop, you update the PD coefficients, and you do the same thing again for 4,000 times. This time is seconds. Yeah, sorry. This time is seconds. Yeah. Yeah, this is seconds. Yeah. Why is my error here smaller? Yeah, so you're comparing this one against this one, right? Okay, you're comparing this one against this one. Yeah, so now in the in the first iteration, I'm just having a uniform value for the value function, right? So that's terrible. From there, if you want to minimize the loss, it's going to take a long time. I mean, even after 6,000 iteration, the best you could do is 0.19 into 10 power minus 4. Yeah. So the easiest way to resolve your confusion is to think of solving from capital T minus delta T every time. So in the next iteration, the new time becomes capital T. Right? Yeah, exactly. Yeah. The one that came out of here. The one that came out of, yeah, you have a much better initial guess now. But what's important here is to notice that this loss here is lower than this one, right? And it keeps monotonically decreasing. Right? At the beginning of every time iteration, your loss is already getting smaller. And the reason is every time I solve this time iteration, I'm basically saving the model. Okay? I have a line here which says model.valuefunction e.save. Okay? And what it does is it's after running for 6,000 iterations, it saves all the weights and parameters of this neural network somewhere in your computer. And at the start of the next time iteration, it just reads those weights and bias. So you have a much better advantage in now. Starting at an initial, you have a much better guess, not just a much better guess for the value function, but also a much better guess for the weights and bias of the neural network. Okay? And in the code, I think once you inspect, you can see that you have an option to remove that condition. Instead of saving and rereading, you can basically retrain the model from the scratch, and you will notice that it takes at least twice as longer to converge. Okay? Total loss. Yeah. And your F loss, correct. All right, so as the iteration progresses, I basically let it run. And oops, where is it? Yeah, after 70 iterations, the absolute max error was less than 10 power minus 5. And so it just stopped and it converged. Okay. Now you notice here that in the beginning, it took a long time because let's go back to the very first iteration. Sorry. And the very first iteration, you notice the seconds, like it took around 73 seconds for the first time iteration to be complete. And progressively, it just keeps reducing. Okay? And the last few iterations are very, very fast. Okay? I think I used my premium account to solve this. So I could solve this in 5 minutes, which is bad compared to finite difference. But then if you solve a two-dimensional model, it's going to take you 10 minutes, and three-dimensional model maybe half an hour. It gives you the ability to solve models that could not be solved using finite difference methods. Okay, that's a good question. For parallelization here, I have not parallelized anything at all, but I do have a couple of slides on parallelization. So I think I'm going to. Yeah, that's right. So I'm showing here. Here you have the GPU accelerator. Right? Everybody gets this GPU accelerator, but what's different is you have this premium, which gives you better power, and you have high RAM. Okay? And for this, you pay $8 per month, which is not bad. But still, you get the problem that it gets disconnected when you're not actively on the page. Oh, GPU can also just make the computation faster. It's not necessarily just for parallelization. Right? Just the computation time of every operations here gets at least 6 times faster than running it on your CPU. Yeah, in the background, something is happening, but we're not explicitly using data modeling, data parallelization or model parallelization. Yeah, typically, I wasn't planning to talk about this, but a short answer is that we typically have a grid. For example, here, the most important training hyperparameter is the learning rate. Okay. For learning rate, we typically have a grid between 0.001 and 0.5. And on a log scale, you randomly sample, on a log scale, you just choose some values between the grid and you repeatedly train the model. And you just choose the one that gives you the lowest error in the end. You basically, for each of this model, you compute this error and you just pick the one that has the lowest error. And when you have a higher learning rate, most likely you'll get some NAN value here and the loss will just explode. So usually learning rate between 0.01 and 0.1 is much better. Okay. And you could do the same thing for the number of hidden layers, so on and so forth. But that's a cumbersome task. Yeah. Yes. So that's where I think the pickles and libraries are useful. You can just save all of this library into your computer, and that's what I did before showing up. And here in this function, you have something called read pickle that reads the model V1. What is model V1? It's here. Yeah, this is model V1. Once you solve this model, you just save it to your computer. You just read it. And let me do this again. And you also solve using finite difference methods. For that, I have a library called model recursive, where it solves this recursive model using a finite difference, implicit finite difference method. Once it converges, you can just compare the neural network solution with the finite difference solution. I'm going to show you qualitative plots, but quantitatively, the error is smaller than 10 power minus 4. Okay. Let's just wait for a few seconds. It's going to be done. So what I'm plotting here is as a function of the state variable, I'm plotting the value function for the experts here and value function of the households. Well, it's a nice bump here. It's a nonlinear function. I think it does pretty well. For households, it's more nonlinear. The neural network method captures it extremely well. Sorry? Yeah, visually it's the same. I think if I have to put a number, it's less than 10 power minus 4, the error between these two. Which, yeah, which I'm happy about because the function looks a bit non-linear to properly approximate. Of course, here I'm also comparing the policies. This is the return volatility, your capital share, and everything, and they also fairly match. So we have 4 more minutes. I'm going to quickly show you how to solve a 2-dimensional model. I'm just going to go through the syntax and yeah, okay. So I'll also spend some time on data parallelization. This is also disconnected. Okay, so let's say you have a 2-dimensional model. Okay, you write similar piece of code, except that now your PD solver is going to take a advection diffusion coefficients of these 2 dimensions as well as the state space. What's different here is that the way you compute partial differentials, sorry, the way you compute df by dz and so on and so forth is slightly different. You not only use tape, but you also use tape 2. But other than that, the concept is exactly the same. You use automatic differentiation to compute these derivatives. Depending on whether the agent is expert or household, you use a different function and you compute the loss residual. This here's the PD solver, which aggregates all of the loss. Oh, yeah, that's a good question. I forgot to mention the decorators at all. So how to make sure that all of this takes computation happens in a graph? Well, you use tf.function. So this converts this Pythonic function into a TensorFlow function. And when you do that, it just sends all of that into a computational graph. And where does actual computation happens? It's in the actual loop here, where you, in the training step, you call these functions and you compute those gradients. Yeah. No. Well, I just showed you because it's important to understand what is this doing. Because, for example, in some cases, you would also have to use this decorator about these functions. Here, that's not required. But in some cases, you do. If you don't want eagerly execution, then you'd want to do that. And that's why it's important to know what this object is. Okay. All right. So in this 2-dimensional model, what's different? Well, nothing much. The only area where things get a bit longer is here, where you compute these derivatives. Apart from that, just compare it with the 1-dimensional code. Everything looks remarkably similar. Okay? If you want to write a 3-dimensional model, it's the same thing, except that your other class where you compute the static PD coefficients may look entirely different because that depends on the problem at hand. But as long as solving the PD is concerned, it's going to be similar to this one. Any questions? I'm just going to talk about parallelization. But if you have any questions on coding convention. Yeah, it's better to write a loop here. Up to 5, I think being a lazy programmer is not a big deal for as economists. So you just keep adding lines here. But more than 10, it just becomes cumbersome. Just write a loop. That's a good point. So here, I'm not using stationary distribution at all. If you want to use stationary distribution, just simulate the model. And yeah, the forward propagation is, again, is super cheap, right? So yeah, I think the only way to do that is to simulate the model. Because this gives you the final solution, right? You don't need the ergodic density to solve the model. Here, you already solved the model. Just simulate and you get the stationary density. Okay. Whereas in the other approaches, at every iteration, you're also simulating, you're also computing the stationary density. Yeah. Let me go back to the slides and talk for 2 minutes about parallelization. Where is it? My God. Oh, no. This one. Sorry. Okay. So there are two kinds of parallelism: data parallelism and model parallelism. What's relevant to us is model. What's relevant to us is data parallelism. What does it mean? You store data here. For us, most of our data is simulated anyway, so it's not like we have massive amounts of data that we can't store in computer. That's not the case. Of course, if you go solve 10,000 state variable problem, then there could be. But let's imagine we have a slightly simpler case. You store the data, and you send it to, and you send the same model to multiple cores. Each block here refers to a core in your computer. You don't need a GPU. All of this can also be done on a CPU. If you have multiple cores on the CPU, send the same model to multiple cores. Each model will receive different data, right? Simulate data and send here, simulate another set of data, send here, so on and so forth. Each model will train on its own. It's going to use Adam optimizer and minimize the loss, compute the gradients. And finally, we have to aggregate the gradients across these cores. And this communication part, this line here, can be a bit nasty. It's not trivial for the cores to communicate across. But let's say we do that, and then we average the gradients, and then we basically update the model. Okay? This is how data parallelism looks like. So there is a nice package called Horvath developed by Uber, and they have made it available open source that gets around this issue. Okay? They have a nice way of letting these cores communicate across each other. It uses something called ring all reduce operation, where instead of cores communicating with every other core in the cluster, it only communicates with the neighboring core in a ring fashion in order to average the gradients. That turns out to be much efficient, but we don't need to get into the details. All we have to do is know how to use Horvath. Okay, here, these two functions we already saw. Here's how you define the neural network. Here's how you define the PD residual. You initialize Horvath here in this line. You have to pin the GPU to the process by configuring, but it doesn't have to be GPU. It can also be just a CPU instead of GPU. Now, the way it works is like there is a chief worker and there are other workers. And you just take the local rank of your cluster and you assign it to be a chief worker. Okay. If it's not a chief worker, then assign a piece of data to each worker. Okay. You first assign a piece of data to chief worker, and then to the other workers. But it's important to know who the chief worker is in order to have a better communication across cores. Once you do that, you just build the model. This build model is exactly the same as what you saw earlier, except that here, when you use the optimizer, this self.optimizer in the previous file used Adam optimizer, which is fine. But in the next line, you have to make it a distributed optimizer. This OPT is basically self.optimizer that we saw in the code. Once you do that, you minimize the loss by calling the training loop, and you initialize the TensorFlow session. Okay. By this, I mean you have this nice function, the decorator function, tf.function, right? You call that, and then you broadcast to the variables across. Okay. This is where the parameters get communicated and they are averaged. And here's, until here, no computation happens. Here, you finally run the session, right? And you train the model. That's it. Yeah, that's correct. So this model will run for each time iteration. There are more efficient ways to do this, to build a static model in TensorFlow as well. But the reason I separated these two out is to let other people just use the PDE solver and write their own model in either NumPy or other packages. Yeah. Yep. Mhm. Yeah, that's a better way to do it. I agree. The reason I don't is because the kind of model that I'm solving involves a fair bit of computation to compute those PDE coefficients. And yeah, that's why I don't do that. But in principle, if you have a simpler model where computing those policy functions are relatively simpler, then write that in TensorFlow as well, so that you just build one big graph where everything is stored. I agree with you. One of the complications here is that the model that I am solving in this paper is to solve the optimal policies, you need to solve a first order partial differential equation for which Newton-Raphson is applied. And there's a lot of stuff going on, which is why I took it out of TensorFlow. Yeah. Okay, so what do I have next? Oh yeah, so one last slide on high performance computing. If you have access to some kind of a cluster, I'm assuming you might at Princeton, this is how it's going to look like. There are many ways to run it. One is the interactive way, and the other is a Slurm batch submission way. But let me just show you the iterative way, which is fairly straightforward. You interact with the cluster. Interact with the cluster. You specify that you want a GPU partition, and you specify the memory. Here I'm using a 120. This is 12 GB memory, but it's recommended to use 128 or 256 if you can. And here's how you mention the time limit. And you create a virtual environment, because in a cluster, lots of users use the same cluster, right? If everybody uses the same Python, then it creates a mess. So typically you create a virtual environment for Python just for yourself, and then you work in that virtual environment. And that's what this does. And you activate that virtual environment and you install the TensorFlow, and just make sure that you install TensorFlow/GPU. And once you type in this into your cluster, this is the output that you get. This is the number of cores you have, tasks, time and memory. This is your partition account. Always make sure to use your advisor's account so you don't have to pay. Job name, blah, blah, blah. Finally, it says job allocated. Okay? Once it's done, just type IPython and your Python terminal opens, and just run your script. That's it. Okay? I'll post a version of this in the Google Drive folder, so you can take a look. Okay, so that's all I had for today. Thank you all for coming. I hope you all enjoyed the mini workshop. I'm here to take questions. A special thanks to Markus for organizing this.